to appreciate just how close this analogy is, let's begin by writing down the electric field for a point charge. So let's take a note here. If I've got a point charge, the electric field from the point charge at any location r, now we've looked at this before, right? It's Coulomb's constant times the charge divided by distance squared, r squared, and then to the power, then multiplied by the outward unit vector r hat. And now certainly this result for the point charge looks a lot like the result that I have here for the velocity from a point source in the fluid. Things don't line up quite perfectly, but I've got all of the key ingredients. And there's something that I can do to really bring out this analogy. I want you to notice that this Coulomb's constant, Kc, is often written in another way. And what I'm about to show you actually explains the reason for this somewhat odd appearing choice. But the Coulomb's constant is frequently also written in terms of a new constant defined to be 1 over 4 pi times this new constant epsilon naught, where epsilon naught is defined to be the permittivity of free space. Now, if I were to substitute in this definition for Coulomb's constant, this new, in terms of this new constant epsilon naught, by the way, you can simply compute epsilon naught in terms of Coulomb's constant K by solving this equation. Coulomb's constant, the permittivity is actually 1 over 4 pi times Coulomb's constant, if you're curious about it. But if we define epsilon naught that way, so that Coulomb's constant can be written in this form, the electric field for our point charge then simply becomes Q is all that's left in our numerator. Our denominator then picks up 4 pi epsilon naught to represent Coulomb's constant. We still have our original r squared, and then of course now this is times r hat. And now you can see the analogy is very, very close. We see that we have exactly the same 4 pi constant. We see that the role of the mass density is the same as epsilon naught in this equation. And finally, we see that the way we can set the current in our fluid model to reproduce exactly the electric field from our electric calculation is to simply pump down the wire an amount of current of mass per unit time equal to the point charge that we are trying to represent. And if we do that, and if we find a fluid, for example, or imagine a fluid where the mass density of this fluid actually matches this fundamental constant of electric theory, then our electric fields will match exactly numerically. We'll be doing exactly the same thing. So we could make this thing in a tank, we can measure the velocity field, and we will know we have exactly numerically exactly equal to what the electric field would be from the corresponding point charge, provided we're pumping the correct amount of current down our hose, that current equaling the amount of charge Q we're trying to represent. So, with that said then, we see there's this nice translation table where we can translate from these two different systems in a way that is mathematically precise or equal. So on one side of this translation table, we're going to have the electric quantities, things in our electric world, if you want to call it that. And on the other side of the translation table, we'll have the quantities from our fluid model or our water world, if you want to call it something like that. We won't think so much about the Kevin Costner movie. It actually, I didn't think was that good. But in any event, electric world and water world, everywhere in electric world that you have a point charge, in water world then, you can get a velocity field matching the electric field, provided at all those same locations you put point sources, our little sprinkler balls. Then also, in electric world, we have this quantity epsilon naught that determines the electric field. And the translation of that in water world is we want to find a fluid whose density would numerically equal the value of epsilon naught. That will guarantee equality in our results. Next, for each point charge, it carries a certain amount of charge Q sub n. In water world, that means that the corresponding point source should have fluid pumped down into it at a rate of a current I, and that I sub n should exactly match Q sub n for each different point source or point charge n. And finally, if you do all of this, we've just shown that you will get exact equality between the electric field that you might be trying to calculate for some complex situation and the flow field in the fluid that you could then actually measure in your mechanical model. And these correspondences can become exact then equalities across this translation table. Let's see how this would apply in an example, and then we're going to use it to pull out this a rigorous result that is extremely powerful and convenient for calculating electric fields in a whole variety of different situations. So I'll try to keep my translation table up here for the beginning part of this analysis. So what I'd like to do is simply to imagine a question in the electric world, and I'm going to use what I know about fluid flow in order to answer it. So we'll practice using our table. So let's imagine I've got a point charge here, plus Q, and I might just tell you, okay, I'm going to take a point charge plus Q, and I'm going to draw around it a sphere. So let me try to draw a reasonable looking sphere. Not too bad. Sphere. And my sphere is going to have a radius r. Typical thing. And now I'm going to ask a question. What will I get if I integrate around this closed sphere the following quantity, epsilon naught times the electric field dotted with the area elements? What would I get? That's the question. Now here's how I would answer it. I could go and start doing some, stick in the value for the electric field from the point charge and then start doing some complicated surface integral, but I want to use my mechanical analogy so I can use my fluid intuition. So what I'm going to do is, rather than answer the question as a direct calculation, let me translate it. This would translate into a certain question in water world. I can carry out the same operation there, and as long as I've obeyed my translation table, I know I'll get the same answer from the water world question. So the water world question would be, what would happen if I were to integrate around this closed surface, not epsilon naught, but rho naught, and not the, because epsilon naught turns into rho naught, not the electric field, but the velocity field, v of r, and I were to integrate that dot dA. Now here in water world, this turns out to be a very easy question to answer, because rho naught times the velocity, you will recall, is the current density J of r. And when I integrate current density, current per unit area, dotted with area, I get the current summed up over all of the patches. So this then is just going to be the total current coming out of this sphere, which in water world is just equal to the current I'm pumping down my hose. That would just be the quantity I. Now here's the neat thing. I've answered the question in water world very intuitively based on conservation of mass. I now that I've answered it, I can translate my answer back into electric world using my translation table. My translation table tells me this current must equal the charge. So back into real world, that tells me, back into the electric world, the answer to this strange looking integral is just going to be the charge Q. So let me just write this down more neatly. So what I'm saying is, if you do a closed surface integral, epsilon naught times E dot dA around this sphere, the answer you're going to get is going to be just Q. And I'm not going to work this out. I don't want to spend the time on it in the video lecture, but it is a great exercise for you guys to go and to check for yourself. And you'll see that our analogy actually holds up extremely well.